The universe often presents us with puzzles, patterns that seem to emerge from the chaos. One such puzzle captivated astronomers for centuries: the seemingly regular spacing of planets in our solar system. In the 18th century, a simple, elegant formula known as Bode's law promised to unlock this cosmic mystery. It offered a mathematical explanation for the distances between the planets and the Sun. This law ignited the imaginations of astronomers, fueling the search for new worlds and deepening our understanding of the solar system's architecture. Bode's law emerged from the meticulous observations of early astronomers, who noticed a curious regularity in the distances between the known planets at the time: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. The gaps between these celestial bodies seemed to follow a specific pattern. Intrigued by this apparent order, astronomers sought a mathematical explanation, a formula that could predict the distances of planets from the Sun. This quest for a cosmic rule led to the formulation of Bode's law, a simple yet powerful equation that seemingly captured the essence of planetary spacing. The idea that a simple mathematical formula could predict the positions of planets was both thrilling and perplexing. Could such a law truly reflect the fundamental principles governing the cosmos? Or was it merely a curious coincidence, a numerical fluke? The scientific community was divided, with some embracing Bode's law as a revolutionary discovery, while others remained skeptical, demanding further evidence and rigorous testing. This debate fueled a wave of astronomical investigations as scientists sought to validate or disprove the law's predictions. Bode's law, at its heart, is a simple mathematical formula that generates a sequence of numbers. These numbers, when adjusted with a specific unit, correspond remarkably well to the distances of most planets from the Sun. The equation starts with the sequence 0, 3, 6, 12, 24, 48, 96, and so on, where each number, except the first two, is double the previous one. To each number we add 4 and then divide the result by 10. The resulting numbers represent the predicted distances of the planets from the Sun, expressed in astronomical units, where 1 AU is the average distance between the Earth and the Sun. This seemingly simple formula produced surprisingly accurate predictions for the distances of the known planets at the time, particularly for Venus, Earth, Mars, Jupiter, and Saturn. The close alignment between Bode's law's predictions and the observed distances of these planets ignited excitement among astronomers, suggesting the existence of an underlying order in the solar system's architecture. The law hinted at a hidden blueprint, a set of rules that governed the arrangement of celestial bodies. It seemed as if the cosmos itself was revealing its secrets, one planet at a time. However, Bode's law was not without its limitations. While it provided accurate predictions for most planets, it notably faltered when applied to the outermost planets. Additionally, the law's origins remained shrouded in mystery. There was no clear scientific explanation for why planetary distances should adhere to this specific mathematical pattern. The lack of a physical basis for the law fueled skepticism among some scientists, who viewed it as a mere numerical coincidence rather than a fundamental principle of nature. Bode's law, despite its imperfections, played a pivotal role in some of the most significant astronomical discoveries of its time. The law's most notable triumph came with the discovery of Uranus in 1781 by the English astronomer William Herschel. Herschel's discovery sent shockwaves through the scientific community, as it revealed a new planet beyond Saturn, the previously known outermost planet. Remarkably, Uranus's distance from the Sun aligned perfectly with the prediction made by Bode's law, further solidifying the law's credibility and fueling speculation about the existence of other undiscovered planets. The law's success in predicting Uranus's position fueled a fervent search for additional planets that might reside in the vast expanse beyond Saturn. Astronomers meticulously scanned the heavens, guided by the predictions of Bode's law. This systematic search led to another significant discovery: the asteroid belt, a region between Mars and Jupiter teeming with countless small rocky bodies. While Bode's law predicted a planet at this location, the discovery of a belt of asteroids instead presented a new puzzle. The discovery of the asteroid belt, while not a perfect match for Bode's law's prediction, nevertheless hinted at the law's influence on the solar system's structure. The presence of these asteroids in the region predicted by the law suggested that some gravitational influence, perhaps related to a planet that once existed there, had shaped the distribution of matter in this region. This discovery further fueled the debate surrounding Bode's law, prompting scientists to grapple with its implications and its role in the solar system's evolution. The discovery of Neptune in 1846 dealt a significant blow to Bode's law. Neptune, the eighth planet from the Sun, was found at a distance significantly different from what the law predicted. This discrepancy challenged the law's universality and raised questions about its underlying principles. The discovery of Neptune highlighted the limitations of applying a purely mathematical formula to complex astronomical phenomena. It suggested that while Bode's law captured a certain regularity in planetary spacing, it did not fully encapsulate the intricate gravitational interactions that shaped the solar system's architecture. Pluto, discovered in 1930, further complicated the picture. Pluto's orbit was highly eccentric, crossing Neptune's orbit at times, and its average distance from the Sun deviated considerably from Bode's law's prediction. Pluto's unusual orbit and its deviation from the predicted distance added to the growing body of evidence challenging the law's validity. The discovery of exoplanets, planets orbiting stars beyond our solar system, offered a new testing ground for Bode's law. With thousands of exoplanets now discovered, scientists have the opportunity to examine whether Bode's law or a similar mathematical formula might hold true in other planetary systems. Preliminary studies of exoplanetary systems have yielded mixed results. Some systems exhibit planetary spacing that roughly aligns with Bode's law, while others show no such correlation. This variability suggests that the factors influencing planetary arrangement in other star systems might be more complex and diverse than those observed in our solar system. Bode's law represents a fundamental human desire to find patterns in the universe. From ancient times, humans have looked to the stars, seeking order and meaning in the celestial tapestry. Bode's law, with its simple mathematical formula, offered a tantalizing glimpse into a hidden order, a set of rules that seemed to govern the arrangement of planets in our solar system. While the law's predictions ultimately proved to be imperfect, its enduring legacy lies in its ability to spark scientific curiosity and to fuel the quest for understanding the underlying principles shaping the cosmos. Bode's law's appeal stems not only from its predictive power, but also from the inherent elegance of its mathematical formulation. The law's simple equation, based on a geometric series, captured a sense of mathematical harmony that resonated with astronomers and the wider public alike. The idea that the universe's structure could be encoded in such a concise mathematical form was both intellectually satisfying and aesthetically pleasing. The law's mathematical elegance fueled the belief that it represented a fundamental truth about the cosmos, a reflection of a deeper, more profound order. Bode's law, despite its limitations, played a pivotal role in driving astronomical discovery. The law's predictions, particularly its success in foretelling the existence of Uranus, motivated astronomers to meticulously scan the heavens for new planets. The search for planets that might conform to Bode's law led to the discovery of the asteroid belt, a region populated by countless small rocky bodies between Mars and Jupiter. This discovery, while not a perfect match for the law's prediction, nevertheless provided valuable insights into the solar system's structure and evolution.